Differential equations. We're on lesson 7.4, day 2. We're now on page 2 of the notes. We're going to look at an inverse convolution. If I took the inverse Laplace transform of capital F of S times G of S, that would be the convolution of f of x and g of x, or accordingly f of t and g of t. Here's what we're talking about. Let's just for a moment realize that what we have right here, this inverse transform applied to 1 over s minus 2, that's kind of like s minus a, or a is equal to 2. You'll have e to the 2x. That would be the convolution of e to the 2x times here, of course, your a would be 3. This would be e to the 3x. But this is really from example 1 on the front page, and we saw that if we worked that integral out, we'd get e to the 3x minus e to the 2x. So rather than work that out in its entirety, we're going to be able to just refer back. As we here, you can see that we can pull the 6 out, but please do remember that ultimately what we're looking for is a product of two inverses. We saw that in example 4, but just want to point out to you that we're looking for two functions, capital F of S and G of S. And I guess s squared minus 1, I think you could quickly see that factors. You can more or less immediately see that it's a difference of squares, and it would factor to s plus 1 times s minus 1. Well, we could separate that. And that can beg the question, well, why in the world would you want to separate that? Well, look at the top of the screen. We want to see a capital F of S multiplied to a G of S. So we're going to have our 6 out in front. And what is this inverse transform of 1 over s plus 1? Well, your a would actually be negative 1 here, so we'd get e to the negative 1x. And then that's going to be the convolution with, well, here a would equal 1. So then we'll have e to the x. Now, at this point, it's very tempting to stop, but we're going to continue on with this integral. We can very quickly say, well, we'll have a 6 out in front. And what's the definition of this convolution? Well, it means set up an integral from 0 to x. And then we'll have our f of t. Here's my f, little f. We're going to have e to the opposite of t. That's f of t. And then we're going to have our g of x minus t. So that's going to be e to the x minus t. And at this point, we just have to work this integral out. Of course, we're going to add these powers together just like we did on the front page. And you can see that that's going to be e to the x minus 2t. And we're integrating with respect to t. Now, guys, of course, just doing some basic calculus review. What you're going to do, of course, is have e to the x minus 2t, but please understand that t is your independent variable. We're going to have to reverse the chain rule. If we took a derivative, the derivative of that inside would be negative 2. So we're going to actually have to divide by negative 2 as we're working this out and applying the fundamental theorem from x to 0. So really we've got negative 3 out in front. That's your 6 divided by negative 2. And then as we substitute x in, again for t, that would be x minus 2x. That's going to leave us with e to the opposite x, minus, as we plug 0 in, again for t, we're just going to be left with e to the x. So right here is, in fact, our final answer. That's that Laplace, inverse Laplace transform that we're working with. So we can use that convolution to help us. As we're looking at the bottom of page 2, They're saying, what if g of t is equal to 1? Well, that's a very special kind of a situation. By the way, I guess I just wanted to tell you, if we had f of x convoluted with g of x, we just saw a moment ago that that would be some nice review. 0 to x of f of t, and then we had our g, of course, is going to be x minus t, and we'd be integrating with respect to t. Well, what if we had f of t convoluted with g of t? Well, you could refer back to the front page. We're going to integrate from 0 to t, but this is where our dummy variable, so to speak, becomes tau. And I'm just, trying to help you remember how that could look just a little bit different. And I know it can look rather strange. This would be a d tau. So, as we're looking at this, you could say, well, what if we had f of t convoluted with g of t. However, the g of t was always 1. So even if we had a substitution of t minus tau in there, we'd still get a 1. That would mean that this inside portion of the integral would just, disappear more or less. So if that's the case, if you ever just saw a Laplace transform of this integral from 0 to t of f of tau d tau, what was it? Well, you can definitely see from what we saw earlier that we would apply our Laplace transforms. If you're applying the Laplace transform of that integral, of that convolution, it would be the individual Laplace transforms multiplied together. So that's really the proof that we're going to get right here. The Laplace transform of g would be 1 over s. That's just the 1. And the Laplace transform of f would just be capital F of s. So that's what we're seeing right here. And similarly, we can go backwards. We could take an inverse Laplace transform and arrive back at this integral of 0 to t f of tau d tau. And that can be special. You're going to see why. As we get to our next video, we're going to see that integrals that have this appearance, like we've just been writing down, can in fact show up inside of differential equations.